Hello everyone, welcome back friends. In last lecture we have seen what is the organic chemistry, what is the delocalized chemical bond, what is mean by resonance, what are the aspects of resonance, how they affect their chemical property, or what are the usefulness of resonance in organic chemistry. Then we will move towards the conjugation, and lastly we have seen in a cross conjugation. Friends, in today's session, we will continue remaining part of last topic, nature of bonding in organic molecule. Friends, in today's session, we will see hyperconjugation, hyperconjugation in toluene, a requirement for hyperconjugation, consequences and application of hyperconjugation, tautomerism, some examples of Keto-Enol tautomerism, and bonding in Fullerene or Buckminster that I little bit explained in last lecture. Friends, hyperconjugation. This hyperconjugation concept you have already learned in your graduation level, but here we revise this concept again. Friends, you have very much known about the inductive effect or electronic effect like mesomeric effect, inductive effect. In inductive effect, there are two effects, that is plus I effect and minus I effect. When electron releases, then we will call a plus I effect, and when electron accept it, then in that case we will call it as a minus I effect. Friends, the normal electron releasing inductive effect, that is plus I effect of alkyl group in the following order. See, the plus I effect goes on this increasing order. Methyl, then ethyl is greater than isopropyl and isobutane. Like that, as come as the electron donating group increases, the plus I effect goes on increases. But it was observed that Baker and Nathan that in conjugated system, the attachment of alkyl group reverse their capability of electron release. Friends, the plus I effect and minus I effect, this inductive effect works only in sigma bond, or purely it works on covalent bond. But when uh, Baker and Nathan that explain this uh, electron donating group, what they affect, then they are conjugated, or the EMTP orbital are in their alpha positions. Baker and Nathan that told us that in conjugated system, the attachment of alkyl group reverse their capability of electron releasing group. They suggested that alkyl group are capable of releasing electron by some process other than inductive method. And how they can share their electron uh, by using this pair of electron or bonding pair of electron. In this hyperconjugation, the carbon hydrogen sigma bond is in the conjugation. The sigma bond electron of this bond enter into conjugation. Friends, this in inductive effect we have seen there is a partial distribution of charges, but in hyperconjugation there is a in hyperconjugation, carbon hydrogen sigma bond enter into the conjugation. In uh, in methyl chloride, what is the inductive effect? We will get delta negative charge on chlorine atom and delta positive charge on carbon atom. Why? Because chlorine have more electronegativity as compared to carbon. That's why the polarization of sigma bond, and they get delta negative charge, and carbon get delta positive charge. But in hyperconjugation, these this concept is not uh, allow, or this concept is completely different in hyperconjugation. In hyperconjugation, carbon hydrogen sigma bond is in the conjugation. The sigma electrons of this bond are entering into the conjugation. Okay, friends, see in this example, these carbon hydrogen bonded electrons are conjugated with empty p orbital, that is pi star cc. This is pi bond, and this empty c orbital antibonding electron. This carbon hydrogen bonded pair of electrons are conjugated with this empty p orbital. See another example we have. Briefly see in this schematic diagram, we will explain all these hyperconjugation concept. This carbon hydrogen sigma bonded electron goes on conjugation with positively charged or empty 2p orbital of carbon. Friends, when carbon hydrogen sigma bond is in the conjugation, the sigma electron of this bond enter into the conjugation. This is an extension of normal conjugation and was termed hyperconjugation. Okay, unlike the normal conjugation, we will see in normal conjugation, they are alternate single and double bond. But in this hyperconjugation, the carbon hydrogen sigma bond electrons are conjugated with empty p orbital of their adjacent carbon atom or any element. Friends, see here, this carbon hydrogen sigma bonds goes on conjugated with empty p orbital of carbon. Unlike the normal conjugation wherein the electrons get delocalized in p orbital, here sigma electrons move to p orbitals. Okay, in normal conjugation we will see the movement of pi bond electron, or these electron are delocalized, but in hyperconjugation sigma bonded electron move towards the p orbital. It involves the delocalization of carbon hydrogen sigma electrons. It essentially means that hyperconjugation depends on the presence of alpha hydrogen atoms. Friends, it is important in hyperconjugation as come as the number of carbon hydrogen bonds are more, their electron donating capability also increases. So that's why it is contrast to plus I effect. We will see in last slide, that is the plus I effect goes on completely opposite to the hyperconjugation. As come as electron donating group increases, the plus I effect increases, but in hyperconjugation this is completely vice versa. See friends, here in methyl group there is a 3 carbon hydrogen sigma bond electrons are present. That's why this methyl group are higher in priority than ethyl. As come as one hydrogen is replaced by alkyl group, their reactivity goes on decreases. Friends, with increase in number of such hydrogen, the electron releasing effect of alkyl group also increases. The contributing structure involving sigma electron of carbon hydrogen bond do not show any covalent bond between carbon and hydrogen. Friends, hyperconjugation therefore is called as a no bond resonance. It is important to note that hydrogen does not actually separate from molecule, because if that happens, the necessary condition for resonance to occur will be violated. Friends, see in this structure, the hydrogen atom does not actually separated from actual molecule. See in this structure, or let's check this example of hyperconjugation in propene. We draw this in schematic diagram. See in this structure, these carbon hydrogen bonds are goes on conjugated with these pi bonds of this carbon, and we will get a positive charge of hydrogen and minus charge on this carbon atom, and we will describe this, or we will rewrite it like a resonating structures. Hyperconjugation exists in molecule having following framework, that is either alkene or carbocation or free radical having at least one carbon hydrogen atom, but not in carbene. Friends, see in all these structures there is a one carbon hydrogen sigma bond adjacent to the pi bonded system. There is a MTP orbital and they have adjacent carbon hydrogen system. In this case, there is a MTP orbital, that is a radical case. In this radical case, their alpha carbon have carbon hydrogen bond. It must require for hyperconjugation case. All these three cases are shown hyperconjugation, but in carbanion there is nothing, any hyperconjugation will be happen. Okay, so there is a requirement of hyperconjugation. There alpha carbon, any pi bond or any MTP orbital like alkene system or a carbocation or carbocation or radical molecule, they must have alpha carbon hydrogen atom. Friends, it is very important point, that is the hyperconjugation in toluene. This hyperconjugation in toluene explain the reactivity of benzene. Friends, see in this schematic diagram, this toluene, that is methylated or methylated benzene ring. You have already known about the toluene. This CH3 group can donate as having plus H effect as it donates or gives electron to the conjugated system. This carbon hydrogen bond, carbon hydrogen sigma electrons are conjugated with this pi system of, or this conjugated system of benzene, and that affect the reactivity of benzene. It also due to this hyperconjugation, toluene are orthopara directing. So this is very important point of hyperconjugation in toluene, and we will describe it in resonating structure. See, this minus charge are delocalized over there, ortho, para, and ortho position. Friends, that's why this hyperconjugation are also affect the reactivity of molecule. The chemical property also changes. Okay, I hope all of you understand hyperconjugation in toluene and what is mean by hyperconjugation, how they can implemented in our chemistry. So friends, next point is the requirement for hyperconjugation. What are the requirements of hyperconjugation? Let's check one by one. There must be an alpha carbon hydrogen group or lone pair of on atom adjacent to the sp2 hybrid carbon, or other atom like nitrogen, oxygen. These nitrogen oxygen are heteroatom and they have lone pair of electron. That's why it must be a requirement for hyperconjugation. For example, alkenes, alkyl carbocation, alkyl free radical, and nitro compound with alpha hydrogens. Then, in that cases, there is a hyperconjugation may be or hyperconjugation happen. Friends, due to presence of hydrogen on the alpha carbon, which is next to the multiple bond, displacement of s electrons, okay, towards the multiple bond takes place, which causes the polarization of multiple bonds. Due to this, carbon hydrogen sigma bond electrons are goes are take part in conjugation. That's why their polarity also changes of that molecule, and that affect the polarization of that molecules. For example, in propane, we will see in this diagram, in propane, the delocalization of sigma bond electrons, the delocalization of propene of sigma bond of methyl group occurs into p orbital of doubly bonded carbon is shown below here. See in this diagram, hyperconjugation in propene, and in orbital format we will shown here. See, all these are the examples. Your hyperconjugation idea will be clear how sigma pair of electron goes on conjugation with pi bonded system or MTP orbital. See in this diagram, this pair of electron goes on MTP orbital of pi bonds or carbon atoms, and this process is vice versa. We will shown here in dumbbell shape, and in this format we will show here banana shape, and this is the hyperconjugation in propane, how they can happen in hyperconjugation in propane. I hope all of you understand this concept. Then we will move toward the consequence and application of hyperconjugation. Friends, what are the application and consequences of hyperconjugation? Due to this hyperconjugation, it affects the stability of alkene. Friends, as you known about that, as come as electron donating group attached to the alkene system, then that alkene is more stable. Okay, in this diagram we will show here one butene and two butene. In 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 these two butene have two electron donating group, but in one butene there is a one electron donating group. So due to this two electron donating group, this two butene is more stable, or we will told as come as electron donating group increases, the stability of that alkene or that butene molecule increases. As general rule, greater the number of alkyl group containing hydrogen atom attached to the double bond, greater is the stability of alkene. This is because of increase in number of contributing number bond resonance structure. So we will can number of resonance structures are increases. Therefore, two butene is more stable than one butene. Then stability of carbocation. Friends, stability of carbocation also due to the hyperconjugation, as the number of alkyl group containing hydrogen atom attached to the positively charged carbon increases, the stability of carbon ion increases because of increase in the number of contributing structures of hyperconjugation. See in this diagram, we will show here number of hydrogen atom increases. As come as the number of hydrogen atom increases, the stability of carbocation goes on increases because of the resonance structure or their carbon hydrogen bonded pair of electron possibility increases, donating possibility increases. See this in this hyperconjugation in ethyl carbonium ion. See the it affects also the reactivity of or uh, carbocation, that is the tertiary carbocation is more stable as compared to secondary, as compared to primary, and in methyl radical. The stability of free radical, same as like in the carbocation, we will told us in stability of free radical. The stability of free radical is influenced by hyperconjugation, just as in the case of carbonium ion. One of the two sigma electrons of carbon hydrogen bond can be delocalized into the p orbital of carbon containing odd electron or a single electron. Due to hyperconjugation, the stability of free radical also follow the same order as that carbonium ions. As I already told that in methyl, then primary, then secondary, then tertiary radical are more stable. As come as the electron donating group are increases, their stability of radical also goes on increases. Friends, due to this transfer of sigma bond electron in conjugation with pi bonded system, their dipole moment and bond length also affects. So that dipole moment and bond length of that molecule changes. The dipole moment of molecule is greatly affected due to the hyperconjugation, since the contributing structure shown considerable polarity. That's why as come as the dipole moment changes, their polarity also changes. The bond length are also altered due to the change in the bond order during the hyperconjugation. So friends, see, in this carbon nitrogen have a bond order different. In after the conjugation, hyperconjugation, their bond order also alters. The single bond might develop partial double bond character and vice versa. The experimental carbon nitrogen bond length is also less than expected value because of same reasons. The reactivity and orientation of electronic substitution on benzene ring. As I already told you, in hyperconjugation in toluene, the due to this methyl group or present on benzene ring, that carbon hydrogen bonds are conjugated with uh, benzene ring, and this due to this conjugation, it affects the reactivity of benzene. See this schematic diagram of hyperconjugation in toluene. As I already told you, and I'll explain all these concepts. Due to this hyperconjugation, the reactivity of toluene also affect. Due to this hyperconjugation, it is a orthopara directive. Then we will see what is meant by tautomerism. Friends, this tautomerism you have learned in your graduation year. So tautomers are isomer of compound which differ only in the position of protons and electrons. Tautomers are constitutional isomers of each other. Friends, the carbon skeleton of the compound is unchanged, but functional group are different. A reaction which involves simple proton transfer in an intramolecular fashion is called as tautomerism. You known about the Keto-Enol tautomerism is a very common process and is acid or base catalyzed. This Keto-Enol tautomerism are acid or base catalyzed. Friends, typically keto form of the compound is more stable, but in some cases the enol form can be more stable. Basically, we will told that the keto form is more stable in keto-enol tautomerism, but like in phenol system, there is a enol form is a more stable, or whenever comes aromaticity concept, then in that form the phenol form or uh, enol form is more stable. In that cases we will see some example of tautomerism, then we will explain how they can more stable than keto form. The keto form and enolic form are in equilibrium, called as a keto-enol tautomerism. Friends, the establishment of equilibrium may be catalyzed by both acids and bases. The how they can keto-enol tautomerism are transformed due to presence of acid catalyze or base catalyze. Due to this catalyzation, we can transform keto to enol formation through the suitable means such as by fractional crystallization or careful distillation of the absence of in the absence of acid or any base, the keto and enolic form may be separated from each other. This is very critical position to separate this keto and enol from, because in uh, in a room temperature they continuously exchange their proton in between enolic to keto form. That's why it is very critical process to separate this keto and enol form. But in some drastic condition, in the absence of acid or in the absence of base, we can separate these keto and enol form. The keto and enolic form of carbonyl compound are constitutional isomers. These are two constitutional isomers. The separation should take place in the absence of acids and bases, as the equilibrium reaction would be otherwise proceed too rapidly. See, in this keto and enol form, we will use a equilibrium arrow because of this process is highly uh, in within a second or very minimum time in between this goes on vice versa process. In this following example, we have shown a phenol and keto form. In this case, we will shown here a phenol form is a more stable as compared to keto form. See in this arrow, here more stable compound is shown in long tail arrow and less stable compound is shown by directing a short tail arrow. Why? Because of after getting enolic form, this compound goes a aromaticity or it get aromaticity. That's why this phenolic form or enolic form is more stable in phenol case as compared to keto. But in other cases, there is a keto form is a more stable as compared to enolic form. Friend, see some, these are the examples of keto-enol tautomerism. This is keto-enol tautomerism. See in this 2,3 dihydronaphthalene 1,4-dione case. In this case, this compound is in keto-enol tautomerism. See in this 1,3-diketone compound in this process, there is a enol form and keto form. As compared to simple acetone, in this case, enol form is more stable. See, all these are the examples of keto-enol tautomerism. Tautomerism occurs in acetophenone or it requires alpha protons. But in benzaldehyde or benzophenone, there is no alpha proton, then there is nothing tautomerism will be happen or it does not occur in like that aldehyde or benzophenone, benzaldehyde or benzophenone because they don't have any alpha hydrogen. It must require alpha hydrogen for tautomerization. For the for tautomerization, we will require alpha hydrogen. If alpha hydrogens are absent, then how can possible tautomerism? So, in this acetophenone and butene 2-ONE occurs tautomerism, but in benzaldehyde and in benzophenone there is does not occur any tautomerism. See this amine and imine form. These are the tautomers of each other. This amide and imidic form. This enol form, this keto form, this lactam and lactim form. All these are the keto-enol tautomerism. I hope all of you understand this keto-enol tautomerism. Friends, then we will move forward towards the fullerene. Friends, this fullerene molecule, as I told in last lecture, that is a conjugated system or conjugation. That is this fullerene molecule, or it is also known as a by another name, that is a Buckminster or carbon C60. Friends, the bonding in fullerene is a very important topic to be discussed here. Fullerene have created great excitement in the organic chemistry world, and in 1991 it was reported to possess remarkable properties of superconductor. As I already told in last lecture, this due to this extended conjugation presence in this fullerene, they shows superconductor properties, resistance, free conductivity at room temperatures also. Friends, X-ray crystallography show the carbon atom are arranged in a layer is a continuous network of planar hexagonal ring. The carbon atom within a layer are held by weak forces and slip over one another. See this see in this diagram, all these are the schematic diagrams of Buckminster Fullerene or Buckminster Fullerene or carbon C60. See in this This bonding in fullerene are extended conjugation have. The newly discovered 1985 allotropes of carbon. This is one of the allotrope of carbon. We have seen in last lecture there is a graphite. It is one of the allotrope of carbon. Then diamond. It is one of the allotrope of carbon. Like that, this Buckminster fullerene also allotrope of carbon, named for two designer of geodesic dome. This uh, Buckminster fullerene named due to there is a geodesic dome in uh, that dome is like that in this fullerene molecule. That's why it is called as a Buckminster fullerene. Unlike diamond and graphite, molecules goes, the fullerene has definite formula of C60. It is known by different names. This fullerene is known as by C16, Buckminster fullerene, and fullerene. Okay, friends. In fullerene, there is a room inside the hollow balls for material. This molecule is very useful for its a special character like superconductor. They have free conductivity at room temperature. I hope all of you understand all the point we have discussed today. Uh, Friends, we will stop here. Thank you. Thank you very much.